I think in the first half of this conference, I've heard limb darkening mentioned with, malice and intent more than I have in the 15 cool stars, stellar systems, and the sun conferences that I've been to in my life. So what's the deal? Why is limb darkening such a big deal right now? Well, the answer is we now have data where it matters. All right, I mean, it does matter for Kepler and TESS, but we didn't have enough to know whether we had limb darkening right or not. We heard on Monday that interferometric observations are sensitive enough now to start testing limb darkening. But JWST light curves spectroscopically getting and needing limb darkening is really what's driving all this. I've listed collaborators, people who have contributed to this, observing programs, software packages, and so on. All played a key role in what I'm going to show you. So limb darkening, what is it? Simply, it's a geometrical effect. If you're looking at the center of the star, you see deeper than if you're looking at the limb of the star, just due to the geometry. And deeper is hotter in the photosphere, and hotter means brighter. It's a function of wavelength, because how deep you see is a function of wavelength. So it's actually a strong function of wavelength. We wind up binning over larger wavelength bins, but it's a strong function of wavelength. And it's a function broadly of temperature as well, because the emission that you're getting, the contrast in brightness, depends on whether you're on the Wien part of the Planck function or on the Rayleigh-Jeans part. So so limb darkening winds up getting parameterized often. There's a bunch of different limb darkening laws out there. All those laws obviously can be violated by the star. This shows the limits of JWST near-infrared instruments, 0.6 microns on one edge and 5.3 on the other. You can see on the left that the slope there is very different, and you can see in the top right what that means in terms of the transit light curve shape. There's a U-shaped bottom in the blue because there's more brightness contrast in the blue, and then it's pretty flat bottomed, but not entirely flat bottomed in the infrared. There are different parameterizations. Popular ones are the parameterization, sometimes called nonlinear. Please don't do that. And then there's the quadratic formulation. And the x's in this plot are a model. The particular one is the MPS model, but it doesn't really matter. And then the three different parameterizations are there. I have quadratic twice, once with an asterisk, because you can apply it differently. Without the asterisk is fitting on the left the actual intensities from the model, which sounds like the right thing to do, but then there are people that like to fit the light curves on the right with the quadratic parameters that best match the light curve on the right, and looking more like your observation, and there's an argument for that. If you know quadratic is wrong, maybe you can cancel errors by working in the light curve space. If you care, everything I show you today will be quadratic with an asterisk. Every quadratic I show you today will be with an asterisk. It doesn't really matter. You will see. And then in the bottom are the residuals. If you do these different approximations, the two different quadratic approximations relative to the 4-parameter, and you can see it's a 50 part per million effect. So that's enough to start mattering, right? That's the point. We have data now that we're getting down to that level. So the dilemma for the community is, do we use the theoretical values or do we use the empirical values? I can't count the number of times people have asked me that question, and there is no easy answer. You need the limb darkening to model your transit light curves. The theoretical values don't always reproduce what you see, as I will show you. Observers then are forced sometimes to solve for limb darkening parameters, which is extra parameters. They have to do it as a function of wavelength, often in fairly narrow wavelength bins. So even though the signal to noise is good, it's not good enough to solve for 4 parameters plus everything else. So they wind up going back to 2 parameters. And yet we just saw the 2 parameters can lead to 50 part per million errors. So it's a dilemma. The community uses both approaches. The choice depends on your data quality, the spectral type, the science goals, et cetera. It's not an easy question to answer. Ideally, ultimately, what we want is we want models that work. I wish I was here today to tell you we have models that work, but we're not there yet, and we need to be aware of that. Reveal was, Sarah introduced Reveal. It's just a project to try to get the 3D MHD models, MURAM plus, out into the community to try to address these problems. I'm going to show you today limb darkening predicted by the 5 first deliveries from the REVEAL project. There's a hydro simulation, which doesn't have magnetic fields. There's an SSD model that you'll see, which is small-scale dynamo, just being formed near the surface of the star. And then there's 3 different field strengths, mimicking a global dynamo. The field is put in at the beginning of the simulation vertically, and then it's run, and it gets all mixed up and complicated. And then on the right, you see for the sun, the simulations actually look a lot like the sun, so that's good. All right, now we're going to talk a little bit about these models. I guess this is the last slide, just looking at the models. So here's all the models I'm going to show you today. There's our Karutz models, which we love, the Phoenix models, which we also love, the MPS 1 and 2 models, which come out of basically the same team that's part of REVEAL, not magnetic. Then there's the 5 I just mentioned. And this is quadratic limb darkening coefficient. So there are 2 coefficients for the quadratic limb darkening. This is G2 star, and I'm imagining it's being observed by the near-spec prism because remember, I'm doing the light curve thing with a quadratic. So, and you can see there's quite a spread in these models, right? So they're not all the same. Maybe not a surprise, maybe a surprise, I don't know. All right, so now for the remainder of this talk, I'm going to put a disclaimer up. These results are preliminary, all right? The measurements and the models that I'm showing you are, hot off the press. They may be refined before they get out into, into press. And my analysis is just the last couple of weeks. I may have made a mistake. There's some improvements I know I could make. But I want to show you these figures because we need to be aware, and it'll be good for stimulating discussion. All right, good. So I'm going to show you a G0 star, a K1 star, and an M4 star, not in that order. This is the G0 star. It's Kepler 12. The data was provided to me by Mons Holmberg. That's the black crosses. It's been binned in wavelength, which is what the horizontal aspect is. And they have some, Bayesian uncertainty, which is what the Y error bars are. And you can see that this is just a single transit, and we can't really tell which model is right. It looks like we might prefer slightly the models that are higher up in this case. You can see if you look closely that the models near the bottom are the ones that have stronger magnetic field, right? So maybe a non-magnetic model works a little better here. You would want to take more transits or compare more stars to really be able to decide if you need to be on the top of that envelope or not. This is on the left side. On the right side, the other coefficient, it's clear the models are not working. So I know you were all looking at the right side while I was saying that. I was looking at the left side. This is not the emperor's limb darkening coefficient. So the right side is obviously systematically off. None of the models are fitting. So if you interpret, you never know for sure. I don't know for sure, let me put it that way. It can be known, but I don't know for sure if the observed values are exactly right or not, but I think they probably are. And so it looks like all the models are off in some way, and the limb darkening parameters are degenerate, as you may know, but usually they go, oppositely like this if it's a degeneracy. If one side is right and the other is off, that means the models don't have quite the right shape. And the sense of it here is that the limbs of the stars are not as dark as the model predicts a little bit. All right, so in this case, I guess I would have to advocate that the folks use, the investigators use the empirical limb darkening because it seems like the models are far enough off that you shouldn't use them. All right, now we're going to skip the K star. We're going to go to the M4 star, which I would have thought would be the worst, but it's actually quite good in this case. All right, this is TOI 3235. The data are provided by Zoko, a graduate student at JHU working with Nestor Espinosa. And you can see it looks pretty good. On the left-hand plot, near 3 microns, you can see that the water, or absence of water, right? The water band, some of the models look a little better than the others. So if you were going to pick a model, you might want to pick one of the ones that describes that a little, matches that water band a little better. But otherwise, the rest of the batch of models looks pretty good. If I were asked what should the investigators do in this case, I would say, well, why waste all those free parameters? Because there's a lot. Every wavelength bin has, 2 limb darkening coefficients. There's more limb darkening coefficients than almost anything else. I would say just use one of the models. And I would love to see a plot like this in the paper when they do that, saying we did this, and it looks like the models are pretty good. So in order to, get a higher information content in the end, we're just going to use the models. All right. Oh, and the Karutz model, I should just comment, the blue one, I mean, it's not matching the M-dwarf because it doesn't have all the water lines. And there's an asterisk in the legend because I'm being naughty. It doesn't even go this cool, and I'm using it when it's, we know it doesn't apply, but I'm just showing you that indeed you shouldn't use the Karutz models at this temperature. It's not a good idea. Nobody will be surprised. Do I have time? No, I don't. I was going to tell a Karutz story, but you don't get it. All right, so the K1 star, in fact, my time is running low. So let me just say, it doesn't fit at all, either side. Maybe some of it is some degeneracy that is being pushed by something subtle. There's 2 sets of crosses because we have, as always, multiple measures of the fitting the data, and so I put them both down just to convince myself and now you that it's not just that one person did a bad job measuring it. These are totally different codes. The only thing in common is they both fit quadratic limb darkening, but the codes are completely independent, and while they don't agree 100%, they both clearly show that the models are not working in this case. I do not know why. So this is disturbing, and in this case, if they ask me, or if I ask myself, what are we going to do in this case? I don't know. I mean, this is so horrible that I don't like either. Oh no, I would say use the empirical ones, but it turns out that some of these curves that are limb darkening curves that are implied by those coefficients, those observed ones, are not physical. They're not physical mostly in the part of the star that's not sampled, but they're basically not physical. Okay, so take-home messages. Limb darkening does need attention, and it's clear the community knows that. JWST now has the precision to start testing these models. There are significant discrepancies. We need more tests, and ultimately we need a better model. Thanks.
So we do have time for some questions, and we encourage our early career peeps, and we'll start in the back.
Hi, Elizabeth from Penn State. Great talk. I have several questions, but I'll just ask one for now. Ultimately, the majority of these limb darkening models, whether empirical or the models themselves, they don't go out all the way towards the limb. They kind of stop at like a mu of like 0.1. How do you think this is affecting our second limb darkening coefficient specifically, since it's more towards the limb, if it's affecting it at all?
Yeah, Nestor has argued, and I think he might be right, that there's such a small amount of time in the transit that corresponds to the exact limb that unless you're studying limb things like limb asymmetries, clouds on the limb, it probably doesn't matter. If you are studying the limb things, then it matters.
So I know in the community there's a big debate about whether you bin your data and then fit it so that you have higher signal to noise so you're able to constrain your limb darkening, or if you stick to like a native resolution when you fit, and so you have larger uncertainties and then bin. What are your thoughts on that?
Yeah, I used to be generally not in this context in the camp of do it at the finer resolution. But it worries me when I see the errors for the really tiny bins pushing up against the edge of the priors. So that would be naughty. If you're not pushing up against the edge of the priors, then I don't know what I don't have a strong opinion at that point. So,
Elizabeth?
Elizabeth Newton, Dartmouth. I was wondering in the M-dwarf plot, there was one feature that was particularly different between the magnetic and non-magnetic models, in which the data fit the magnetic ones better at like 3 microns maybe. And I guess I was wondering generally if you had an intuitive physical explanation for what the spectral differences are.
Yeah, I think the ones that don't fit well, they are non-magnetic, but there are non-magnetic ones down in the bottom bump as well. So I think this is driven by opacity, just what water lineless they were using.
Okay, we have a final question online, and Nathaniel.
Are those limb darkening models tailored to the specific chemical abundance in log G for the star?
The ones I'm showing are for, so for the G0 star, there was an asterisk because I was using G2 for the reveal models, because that's what I had handy and I was too lazy to extrapolate. But otherwise, yes, they're all interpolated to the particular parameters of the star.
All right, let's thank Jeff again.